Question 38. So it's giving us a redox reaction that occurs in the human body. So we've got NAD is a vital coenzyme for energy production in the human body. It exists in two forms, an oxidized form, NAD+, and a reduced form, NADH. Okay, and it's involved in the conversion of ethanol. So it tells us that the overall equation for this redox reaction is ethanol plus NAD plus will give us here ethanol and our NADH plus our hydrogen ion. So if we have a look at our equation, it gives us some information above here. So we've got here, this is our oxidized form, the NAD plus, and our NADH here is our reduced form. So that tells me if it's going from our oxidized form to the reducing form, that it must have been undergone reduction. Okay, it tells me that from this information up the top. Or if I have a look at it here, I've got my NAD plus and an NADH on the right. Okay, that shows me that it's gained an electron. Okay, and if we remember that reduction is gain. Okay, so just looking at this equation here, even before we get to the questions, I can see that the NAD plus is reduction and my ethanol is being oxidized to ethanol. So then if I look at I, write the two half equations. So if you remember, half equations are our oxidation and our reduction equations, showing our electrons. For this redox reaction, and it says states not required. Okay, so let's have a go. I've already identified what's undergoing reduction. Okay, so all I've got first for my reduction is NAD plus, and it's forming, what is it forming? Okay, NADH. Okay, so remember back when we were, looks like an O, but it's a D, when we were balancing our redox reactions, we go through the stages. So K was look at the key elements, okay, they're balanced. Then we needed to balance our oxygen by adding water and then hydrogen and so on. So there's no oxygen in here, so I don't need to add any water, but I've got an uneven number of hydrogens, so I need to add a hydrogen ion here, H plus. Okay, good. Okay, so now I've got NAD plus plus H plus gives us NADH. Okay, so that's the key elements balanced. Now I need to look at the electrons. Over here on the left, I've got a charge of 2 plus, but over here on the right, it's neutral. So remember, I want to balance the number of electrons, so it's the same on both sides, and I do that by adding electrons over here because they're negative. So we've got 2 electrons. So we had our 2 positive plus our 2 negative would give us a neutral charge, overall 0, and our NADH is 0. So my electrons are balanced. So that's my reduction equation. Then I need to write my oxidation equation. So if NAD plus was undergoing reduction, that must mean my ethanol is undergoing oxidation. So I've got CH3, bear with me, CH2, OH. Okay, gives us, what have we got? I'll leave a gap just in case we need to have a look at it. CH3, CH. Oh, okay, right. Okay, so we'll look at our key elements first. So I've got 2 carbons, 2 carbons. Yep, so the carbons are okay. Got 1 oxygen, 1 oxygen. Then I've got 3, 5, 6 hydrogen here, and I've got 3, 4 hydrogen here. Okay, so I need to balance my hydrogen. So I'll do that by adding 2H plus. Okay, so that's my elements, key elements balanced. Okay, good. So now then I need to look at making sure my electrons are balanced. So this is neutral, and I've got a 2 positive charge here. So then this has to be adding 2 electrons. Okay, and that's my 2 half equations. Second question, identify the reducing agent in this redox reaction. Okay, so reducing agent, remember, is the species that causes reduction. Okay, so if I go back to this equation, I know that NAD plus is being reduced to NADH. I wrote the reduction equation. But what's causing that reduction? Okay, so the reducing agent is my ethanol. Okay, that's what's causing my NAD plus to be reduced. Okay, so that's my ethanol. Okay. Okay, part B to the question. It says the Daniell cell, a type of galvanic cell, was first constructed in the 1800s. A diagram is shown below. Okay. Label the polarity of the electrodes by placing a positive or negative sign in each of the circles next to the electrodes on the diagram above. Okay, so if we remember Daniell cell, we will hopefully remember, and I should have grabbed the electrochemical series, that my zinc is oxidized and my copper is being reduced. Okay, so I would have my zinc is an anode, my copper is being reduced. Okay, now we'll label the polarities. Yep, okay. So if I couldn't remember that, you would have a look at your electrochemical series in your data booklet, and you will see that copper is above the zinc in the electrochemical series. I should have put it included. So because of that, the species on top, remember that as you go up, is a stronger, give me 2 seconds. Okay, so just added the electrochemical series. So if we have a look at our electrochemical series, we've got copper here and we've got zinc. So remember, as we go to the top of the electrochemical series, we've got the stronger oxidizing agent. So copper, remember, stronger oxidizing agents will undergo reduction. Copper will be reduced and our zinc will undergo oxidation. Okay, so remember it's occurring this way. Okay, and then that's how we will know, if we can't remember, that our zinc is at the anode because zinc will undergo oxidation and our copper is at our cathode. Okay. Question 2, I needed that information anyway. We need to use the electrochemical series to determine the theoretical voltage of this cell. So if we remember, if you grab out your data booklet, we need to have a look at the values. So remember, it's the value of the higher cell first, so in this case 0.34, subtract the other one, 0.76. Okay, so I've just taken this value here, and I've subtracted it from the value of the other half cell. Okay, and that should give us an answer of 1.10 volts. Okay, so it's always the higher half cell, subtract the lower half cell. Question 3, the electrolyte in the salt bridge is a potassium nitrate solution. In the box above the salt bridge, use an arrow to indicate the direction of flow of K plus ions. So remember, K plus is a cation, nice and easy to remember. The cations will always move in the direction of the cathode. IV, list 2 visible changes that are likely to be observed when the Daniell cell has been operating for some time. So as my Daniell cell is operating, I would be expecting, remember here, that our zinc is being oxidized, our copper is being reduced. So what's happening is we've got, if we look at this equation here, we're going from copper 2 plus and it's being reduced to copper solid. Okay, so something visible that would occur is that my copper electrode, because it's being reduced, electrode will increase in size. That doesn't even look like the word electrode. Anyway, so because it's being reduced, the copper electrode will increase in size. Whereas, on the other hand, my zinc electrode will decrease in size. Okay, and that would get me the 2 marks. So copper electrode increase in size, my zinc electrode decreases in size. You needed to say that it was something visible. So if I said the copper electrode mass increases, that's not something that I can visibly see. Okay, so if I kept it simple like this copper electrode increases in size, that is something I could visibly notice during the experiment. Question C, what design features of the Daniell cell structure would allow it to produce electrical energy? So if you remember when we were talking in class about how they wanted to take the galvanic cells and develop primary cells into the one container, and we talked about what features allow a galvanic cell and a primary cell to generate that electricity. So the features of the Daniell cell that allow it to produce the electrical energy is we need the half cells separated. Okay, we can't have the oxidizing agent and the reducing agent in contact with each other. Okay, so they're in two separate beakers. They're not coming into contact. Okay, that means that the electrons are forced to flow along the wire. The next design feature is that you need a salt bridge connecting them. Okay, and a few of you observed that when we did the experiment in class, because you saw that without that salt bridge, you weren't getting any current reading. Okay, because that flow of electrons couldn't occur because the circuit wasn't complete.